Welcome back, everyone. And so for this segment of the lecture, let's go ahead and start a hypothesis test, in particular a single sample z-test. So let's start with some sort of context. So let's say we work for Applebee's, and Applebee's wants to implement a new training program. They would like to measure the program's success by comparing the performance appraisal of 30 randomly selected and recently hired employees who've recently finished this new training, and we want to compare it to the last performance appraisals of all employees. So these performance appraisals will be on a scale of 0, very poor, to 100, which is excellent. So notice a few things here in our scenario. It looks like we are randomly selecting, and it looks like we're randomly selecting recently hired employees, which is pretty smart, because if we use current employees, then they might mix the old training that they received when they were hired with this new training. Whereas if we get newly hired employees, ones that are just hired, then they're not going to be confounded with the old training. So we want to compare these recently hired employees and their performance to the performance of all employees. And so that's kind of the scenario that we want to work with, and so we want to test, is there a difference in this new training program compared to the old program that all the other employees have. Now there are several steps for hypothesis testing, and I'm not going to ask you to memorize these steps. I'll help walk you through them when it comes to exams and handouts, but you should know what happens at each one of these particular steps. And so we'll talk about each of these steps in class here and in lecture. We'll get to the first 3 steps today, and we'll finish up steps 4, 5, and 6 in the next lecture. But the steps for hypothesis testing are, first, we need to identify the populations, the comparison, and the assumptions. We then should state our null and our research hypotheses, which we've talked about before in a previous lecture. We then need to identify the measures of central tendency and variability that we're going to use for our test. Once we have those measures, we'll then determine the critical values, or the points, or the point at which we're going to say that there is or is not a difference among our new training in our old training program. We're then going to calculate the test statistic itself, the z-statistic, and we'll use that z-statistic to make a statistical decision based on the critical values that we predetermined before we did the calculations. And of course, what's not mentioned up here is step number 7. We'll take our evidence from our statistical decision, we'll compare it with all the evidences that we have that may be important, and we'll make a practical decision. So those are the steps for hypothesis testing. We'll cover the first 3 in this lecture, and we'll save the last 3 for the next lecture. The very first step in hypothesis testing is to identify the populations, the comparisons, and the assumptions. And so we're always comparing populations. So even though we collect sample data, the whole reason why we collect sample data is to infer back to populations. So the actual comparison is in the populations, not in the data that we collect. So we always compare populations to each other. In this particular case, we have 2 populations that we're comparing. So what are those populations? If we go back to the scenario slide, we can identify the 2 populations that we're comparing. So in this case, we see that we have all employees with the new training measured on their performance appraisals compared to all employees with the old training measured on their performance appraisals. And so there's our 2 populations that we'll use for comparison. Now when it comes to exams and to handouts, I'll ask you to write out the population descriptions. And so that's not new. We've been doing that for the last 2 modules, so this shouldn't be too hard for you. You should have this down already. So we have one population, which is the performance on a 100-point scale of all employees at Applebee's. Our second population is performance on a 100-point scale of all new employees at Applebee's with this new training. And so there's our 2 populations. Now you'll note that the second population here is the one that we're going to infer from our sample. So we didn't actually measure all new employees at Applebee's with this new training. We only measured a random sample of 30 of them. So we're going to infer this from our sample. The other population, we'll gather that information from the last performance appraisal at the end of the year. And so we already have those data already for all of our employees. And so that becomes our population information. We're now going to give this new training to our sample of 30 employees, and we'll infer from that sample back to the population of all employees who received this new training. So one population we have, the other one we will infer from the results of our sample. The comparison itself will be the performance scores between the two population distributions. The population distribution of performance scores based on the old training versus the performance scores on the population distribution of the new training. Whenever we calculate statistics, we make assumptions. Hypothesis testing is no different. So every test that we learn this semester will have its own set of assumptions. Some of those assumptions will be the same from test to test, for hypothesis test to hypothesis test. So in fact, the very first three assumptions here that are listed in this list are going to be the same for most of the tests that we run this semester. I will ask you to memorize the assumptions for each of the tests and be able to identify whether or not we're meeting those assumptions. Alright, so the assumptions for a z-test are that the dependent variable is scale. So in other words, the variable that we measure, in this case performance, is an interval or ratio variable. Our participants should be randomly selected from the population of interest, so we should be randomly selected from the population. Another assumption is that the population is normally distributed, and we should know about that assumption by now. We've used it for z-scores. Normal distribution is one of those assumptions that almost every statistical test that we calculate has. And the last assumption is that we need to have the parameters for one population. What we mean by parameters is that we need to have the mean and standard deviation for one of the populations. And if we do, then we can calculate a z-test. So let's go back, let's look at our scenario and see if we're meeting these assumptions for a z-test. Remember, our very first assumption is whether the dependent variable is a scale variable. In other words, is it interval or a ratio? So the dependent variable is the variable that we're measuring. So we're measuring performance, it looks like, and we're measuring performance on a scale of 0 to 100. And so because it's a scale, as a response scale, we'll have an interval or a ratio variable. So let's go ahead and identify what type of variable we have here. So we'll look at the 0 point, and it looks like 0 represents very poor performance. So very poor performance is not the absolute absence of performance, so we know it's not a ratio variable. So it appears like this is an interval variable. And that's okay because an interval variable is still a scale or continuous variable. So it looks like we're meeting that assumption. By the way, the dependent variable being scale is what we call a necessary assumption. That if we have a nominal or an ordinal variable, we cannot do a z-test. So it's a necessary assumption. Our dependent variable needs to be scale. Alright, our second assumption is that we have random selection from the population. So remember, we have two populations here. We have a population that's being inferred from a sample, so that's the one we want to be concerned with. So our sample is coming from recently hired employees with this new training. And based on the scenario, it says that we randomly select 30 newly hired employees with the new training. So it looks like we're meeting our random selection assumption. Now that is not a necessary assumption. We can have convenient selection or convenient sampling, and we could still continue with our analysis. We just have to be careful about how we generalize back to the overall population. Okay, so our next assumption is the normal distribution assumption. And so here we actually don't have any data to tell if we have a normal distribution in the population. Remember that we only gave 30 of our newly hired employees this new training. The rest of our newly hired employees received the old training. And so our population is a theoretical population of employees who would receive this new training and haven't. And so we actually don't have all the data there to determine a normal distribution. However, because of the central limit theorem, we can make the assumption that we have a normal distribution because we have 30 or more individuals in our sample. And so we can say that based on the central limit theorem, that we have a normal distribution because our sample size is 30 or greater. In this case, it's 30. So we can make that assumption that we have a normal distribution. The last assumption is the parameters of one of the populations. In other words, the mean and standard deviation for one of our two populations. And so that would actually come from our employees with the old training, as far as that getting those parameters, and we can get those based off of the last performance appraisal that they've had the previous year, or the annual performance appraisal that we have on record. And so we would have access to the parameters of each one of the populations. In other words, the parameter for the mean and standard deviation for those employees with the old training based on their previous annual performance review. And so we'd meet that assumption as well. By the way, that last one, the parameters of one of the populations, that is a necessary assumption. if we don't have both a mean and a standard deviation for one of the populations, then we can't do a z-test. Once we've identified the populations, the comparison, and the assumptions, we then need to state the null in the research hypotheses. When it comes to stating the null in the research hypotheses, we have to identify a difference statement. We need to specify who or what is being measured. We need to identify the measurement itself, and we need to also identify the groups that are being compared. So in this particular case, because we haven't talked about one or two-tailed test, we'll just talk about it in terms of a two-tailed test. We'll say that there is a difference or no difference, and the who or what in this case will be Applebee's employees. The measurement itself will be on performance, in other words, the performance appraisals on a scale from 0 to 100. And then finally, our groups are employees with the new training versus employees with the old training. So we can go ahead and write those out. And so we have a null hypothesis that says there is no difference in performance of Applebee's employees between the new and the old training programs. So again, the null is specifying that there is nothing going on, that this new training has no effect on performance. And then we'll contrast that with the research hypothesis. The research hypothesis will state that there is a difference in performance of Applebee's employees between the new and the old training programs. And note here in the research hypothesis, we're not specifying a particular direction. We're not saying performance will increase or performance will decrease. We're just saying there is a difference in performance between the employees with this new and this old training program. So when we talk about analyzing the success of a new training program, it could be successful or it may not be successful. So it could go in either direction. And so we're going to do what's called a two-tailed test. And we'll just say that there is a difference. We won't specify whether that difference is an increase or that difference is a decrease. So there's our null and our research hypotheses. And let's make sure we can identify each of the components that are in a null and a research hypothesis. So remember, there's 4 things that need to be included in a null and a research hypothesis. And so you'll be graded on these 4 things when you write your null and your research hypotheses. The very first thing is that we need to have a difference statement. And so you see in red here, there's our difference statement. We can say there is no difference for the null hypothesis, and we can say that there is a difference for the research hypothesis. We also need to specify what is being measured, and so in this case we're measuring performance. We also need to indicate who specifically is being measured. In this case we're talking about Applebee's employees, and so we want to make sure that Applebee's employees are in both of our hypothesis statements. And we want to briefly describe our groups. In other words, what is our comparison? So in this case, we're comparing the new and the old training programs. So we want to specify what our groups are, what our comparisons are, also in each of our hypothesis statements, both for the null and for the research hypothesis. Once we have stated our null and our research hypothesis, we then need to identify the measures of central tendency and variability for our statistical tests. When we talk about the measures of central tendency and variability, what we're really asking for is, do we have a mean and a standard deviation for one of our populations? In other words, the population that we're not inferring to. So in this case, that would be the population with the old training. And so if we're Applebee's, we can go back and we can look at the last performance appraisal review and get an overall average and a standard deviation for all employees in our organization. And so let's say we go back and we do take a look, we look at our records, and we find that at the last performance appraisal, the average performance appraisal for all employees with the old training was a mean of 72 on our scale with a standard deviation of 12. And so there we have a measure of central tendency, the mean or the average, and we have a measure of variability, the standard deviation. So the question becomes, do we need to calculate a standard error? And in this case, the answer is yes, because we're using a sample to compare to an overall population. So remember, we have 2 populations. One population is inferred from a sample. The other population, we have the data already, so that's the employees with the old training. But we're going to infer from our sample of 30 with the new training. So whenever we have a sample, we need to calculate a standard error. So we're going to take our sample of 30 with the new training, we'll get an average for our sample of 30 with new training, and we'll compare to a population distribution of means made up of sample sizes of 30. So if I have a sample of 30, I need to compare it to a population distribution of averages or means made up of the same sample size. And so I need to calculate a standard error to make that comparison. So to calculate a standard error, we can use our formula, sigma sub m, standard error. equals sigma, which is the standard deviation, divided by the square root of n. Remember, n equals the number of observations in our sample. So in this case, we can take our standard error, which equals our standard deviation of 12, and we divide by the square root of 30, which is in our sample. So here's our formula. We can take 12, divide by the square root of 30, and that will give us the standard error. Once we do the calculation, we get a standard error of 2.19. So notice that our variability decreased from a standard deviation of 12 to a standard error of 2.19. And if you remember, based on the central limit theorem, that's what we would expect. That if we can get samples, we can reduce the variability by averaging out the performance of those in our sample. So when we have a sample of 30, we're going to have some employees who are going to have very high performance. And then we're also going to get some employees that are going to have very low performance. And so we can reduce that variability by averaging. Those with high performance will cancel out those with low performance. And that reduces the variability, reduces the error in our measurement. And so here we can estimate in the population that the standard error on a population distribution of means is 2.19 performance ratings. So our second question is, do we need to calculate a new mean? So we're going from a distribution of scores to a distribution of means. Do we need to calculate a new mean? The answer is no, we don't, again, based on the central limit theorem. So the central limit theorem will tell us that the means will stay the same. So the mean on a distribution of means will be the same as the mean on a distribution of scores in the population. So mu sub m equals mu. And so our population mean for old performance will stay the same. So a 72 on a distribution of scores, it'll remain the same as 72 on a distribution of means. So our parameters for step 3 will be a mean of 72 with a standard error of 2.19. So we can say on a distribution of means in the population where we have employees with the old training that the average rating will be 72 and the standard error will be 2.19 when we have samples of 30 observations at a time, or samples of 30 employees at a time. So that gets us to the very first 3 steps of hypothesis testing. We'll cover the last 3 steps, determining critical values, calculating a test statistic, and making a statistical decision in the next lecture.